So page 58, Polynomial Inequalities. I'm going to finish off section P5. All right, when you solve a polynomial inequality, it's different than a linear inequality. If you have x to the first, y to the first, something that we're talking about, linear equation, going to graph as a line. If you have an inequality that looks like that, we said you solve it exactly like you would an equality, unless you multiply or divide by a negative, and then you have to reverse the inequality sign, right? Okay? But if I'm solving a polynomial or a rational inequality, I have to do those totally differently. I have to make something called a sign graph, all right? So step number one, we're going to set this polynomial equal to 0. So we're going to treat it just as if it was an equality. So if up here I had x squared minus x minus 6 is equal to 0, and I were solving that, I could either factor or do completing the square or quadratic formula, whatever you want to do. In this case, factoring worked, so that's probably the fastest, easiest way to solve this. When I solve it, the solutions that I get are my critical numbers, and I'm going to use those critical numbers to make a sign graph. So I'm going to come over here and plot a number line, and I'm going to plot those two critical numbers that we just got, -2 and +3. Now, those critical numbers just divided my number line into 3 intervals. I have one interval that's going from -infinity to -2. I have another interval that's going from -2 to +3, and I have another interval that's going from +3 to infinity. I can test any number within an interval, and if it's positive, that means that any other number I would test in that interval would also come up positive. If I test any number in an interval and it comes up negative, then any other number in that interval is going to come up negative. Let me show you what I'm talking about. Probably the easiest point to use for a test point is 0. So if I take 0 and I plug it back into that polynomial, that would be 0 squared minus 0 minus 6. So 0 squared minus 0 minus 6 is going to give me a -6. I honestly don't even care about the 6. I just care about the fact that it's negative. So I'm going to come down here and say, okay, when I tested 0, I got a negative value. If I had plugged in any other number in that interval between -2 and +3, we could all go around the room and every one of us pick a different number, fraction, decimal, whatever, within that interval, and every single one of them would get a negative value. Not 6, but they would get a negative value. So I can use one value as a test point to see what that whole interval will be. All right, so then I could do the same thing over here for the interval from +3 to infinity. So maybe I want to choose like +4 and plug that in. So if I choose +4 and plug that in, that'd be like 16 minus 4 minus 6. I don't even care what the number is, just that it's positive. So if one value plugged in gave me a positive value, then any value that I plugged in that interval would be positive. I could do the same thing, come over here to this interval from -infinity to -2 and pick anything I want, -3, -4, -27, whatever you want to choose, and plug it in. And when I do, I'll get a positive value. And so I've created my sign graph. Now, something that we might notice about our sign graph is it basically just alternates, right? Plus, minus, plus. Was that coincidence, or will it always do that? Well, for a sign graph, my sign will change at every single critical number. Now, sometimes we have a double root or a triple root or something. We'll talk about that in just a minute. But if it's just a single critical number, I only got that answer over here one time. There's just a single root there. Then, yes, my sign will change. So I can save myself a little bit of time and energy. If I go through and I plug 0 in and I find out it's negative, if I know that about sign graphs, then I could go through and say cross a single root, the sign's going to change. Cross a single root, the sign's going to change. I wouldn't have to test every single interval. Okay, so I set my polynomial equal to 0, I solved and got my critical numbers, and then I used those critical numbers and some test points to make a sign graph. Now how do I get my answer from that? Well, if I go back to my original problem, The original problem said, tell where that quadratic is less than 0. What kind of numbers are less than 0, positive or negative? Negative, right. So it's asking me, where is this polynomial less than 0? Where is it negative? So if I go back to my sign graph and I look at the negative piece was right here in between -2 and +3, then that is my solution, between -2 and +3. So one more time, if I'm looking for where this is less than 0, I can say what kind of numbers are less than 0. They're negative. That means I want the negative piece off of my sign graph. So we went over to the sign graph and said it was negative in between -2 and +3. And because it was less than, we're using parentheses. If it had been less than equal to, I would have been using brackets. Okay, so I understand the steps, but what in the world did I just find? Well, if I had actually graphed that parabola, x squared minus x minus 6, it would take a whole lot longer to graph it than it would to just make it sign graph, because I have to be precise. It's not just knowing where it's positive and negative, but I would have to know the exact y value. I'd have to know if it was a -6 or a -12 or a -2 or a +7 or whatever y value went along with it, and then I would be plotting those points to generate that graph. When I generate that graph, if you'll notice, from -infinity to -2, that graph was positive. From -2 to +3, that graph was below the x-axis, so it was negative. And then from +3 on to infinity, that graph was above, so it was positive. So what my sign graph does is it enables me to figure out where the graph is positive and negative without me having to make the whole graph. I don't really need the whole thing. I just need to know if it's above or below the x-axis. If by chance I had my graphing calculator on a question like this, I absolutely could just throw this into my calculator and look at the graph and see, okay, where's it negative? Where is it below the x-axis? And I would be able to see that's from -2 to +3, and I could give that same answer. Right? What if instead on this problem, instead of them asking me where is it less than 0, what if they had asked me where is it greater than 0? What kind of answers are greater than 0? Positive. So that would mean that they would want me to give the positive pieces in that case. So there were two positive pieces, right? There was the piece from -infinity to -2, and then there was the piece from 3 to infinity. So if they had asked me to tell where this was greater than 0, meaning where is it positive, then I would have given both of those pieces, all the values less than -2 and all the values greater than +3. So again, although this is in the prerequisite section of things that we're expected to know and be proficient with, this second half of this lesson always seems to be something that you're not as familiar with, and so we want to pay particular attention to it. Okay, so that's how normal polynomial inequalities will work. I wanted to show you a couple of abnormal things that can come up so it wouldn't bother you if you came across this on homework or on a problem that you were working. The next example, we've got x squared plus 2x plus 1 is less than or equal to 0. So we start off by solving that, and again, that would factor. So you could factor completing the square, quadratic formula, whatever you want to do. But this time when I get my solutions, I get x equals -1 and x equals -1. I get the same answer twice. That's significant. That means that I have a double root at -1. If I got that same answer 3 times, I would have a triple root at -1. If I got that same answer 4 times, I'd have a quadruple root there. It matters for my sign graph. So I could come over and I could do as we did last time. I'm going to plot that, and I'm going to make myself a note that it's a double root. And then I'm going to pick a test point to figure out how to fill in my sign graph. So 0 is a really easy point to test. So I'll take 0 and plug it in. So 0 squared plus 2 times 0 plus 1 is going to give me a positive. So at 0, I know this is positive. That means for that whole interval from -1 to infinity, that whole interval is going to be positive. If I picked a test point on the other side, so this interval over here from -infinity to -1, If I picked a test point somewhere over there like -2 and I plugged it in, I would also get a positive. Now remember we had said that sign graphs will change signs at every single critical number. This was not a single critical number. There were two of them there, right? It was a double root. So in essence what happens is it's as if I'm approaching that double root and I'm coming in positive. And I hit the first root and I change to negative. I hit the second root and I have to change again, right? And so it changes back to positive. So at a double root, my sign literally changes twice. So it looks like it doesn't change at all. What if I had a triple root here? If I had 3 roots here, would it look like I had a sign change or not?
Yes.
Yes, because if there are 3 roots here, let's say I'm coming in positive, I hit the first one and change to negative, hit the second one, change back to positive, hit the third one, change to negative again, right? So there's an easy way to sum this up. If you have an odd number of roots at a particular spot for our sign graph, so if I have a single critical number or a triple critical number or 5 critical numbers that are all identical in the same spot, it's going to change signs, and it will appear on the sign graph that it changed signs. If I have an even number, like we had here, the double root, or we had a quadruple root where you had an even number of critical numbers occurring at the exact same spot, the sign is changing. It's changing multiple times, but it will appear to not change at all. Okay, so odd, I will see a sign change. Even, I will not. Okay, so to answer the question that was asked, they asked me, where is this less than or equal to 0? So what are we looking for, positive or negative? Less than or equal to 0, what are we looking for? Positive or negative? Yeah, negative. And it also could be equal to 0, right? So if they say where is it less than or equal to 0, we're looking for negative or equal to 0. So if I come back up here and I look at this number line, there's nowhere it was negative, right? And the only place that it was equal to 0 was right over here. Remember we set it equal to 0 and solved? The only place that it was equal to 0 was at -1. So that is my only solution. And that's kind of strange because typically when we graph these, we get like an interval for our answer. So it seems peculiar to us when we just get a singular number. But look at the graph. If you look at the graph, it backs up what we just found. If I had graphed x squared plus 2x plus 1, this is what my graph would look like over here. So if I'm looking at that and saying, where is it less than 0? There's nowhere it's below the x-axis. And if I'm saying, where is it equal to 0? That's an x-intercept, right? And there's one right there at -1. That's the only one it has. So graphically, we can see it backs up what we had just found algebraically. All right. Here's another one that's a little bit strange. If I solve x squared plus 3x plus 5 is less than 0, I'm going to get imaginary solutions. You could work that out by quadratic, completing the square, whatever you want. You don't even have to write that out. You can just write that you would get imaginary solutions. As soon as I get square root of a negative number, I know that's going to happen. So if I have imaginary solutions, there's no way to graph imaginaries on a number line, right? Later on in the year, we'll look at an imaginary number plane and deal with that. But at this stage of the game, when I'm working with the regular Cartesian plane, X, Y, real number line, any of those scenarios, if my only solutions are imaginary, I can't graph something imaginary. That means I have no solution. So since my solutions are my critical numbers, I have no critical numbers. So if there's no critical number to divide up this number line, that means either the entire number line is positive or the entire number line is negative. So I'm still just going to pick a test point to see what it is. So if I take 0 and I plug it into this thing, 0 squared plus 3 times 0 plus 5 gives me a positive. Again, no critical number to make it change signs. So that whole number line, negative infinity to positive infinity, the whole thing is positive. So if they asked me, where is this less than 0, what are we looking for, positives or negatives? Negatives. So where is this thing negative? It isn't. So that one would be no solution. And so again, I wanted to just go over with you some of the stranger answers that you might come across or some of the alternate scenarios you might see. If you look at the graph of this one again, we understand why we got no solutions, no x-intercepts, because there weren't any. And if we were looking for where this thing was less than 0, we can see why we got no solution for that, because there is nowhere that it's below the x-axis that it's less than 0. What if they had asked me on this one, instead of where is it less than 0, what if they had said where is it greater than 0? What would my answer have been? All real numbers, exactly. Because if I'm looking for where it's greater than 0, where it's positive, that's the whole number line, right? Negative infinity to positive infinity. So when we're doing our homework tonight, 45, 47, 49, and 51 are going to correspond to these types of polynomial inequalities. The second type of inequality that we want to look at today are rational inequalities over on page 61. Rational inequalities. Rational, root word is ratio, right? Something written as a fraction. So here are the steps that we want to follow when we're working a rational inequality. Now this one I went ahead and wrote out for you in your notes so that you could just watch and wouldn't have to keep going back and forth. For a rational inequality, you want to start by moving everything to the left-hand side. So sometimes when they give you your problem, it automatically looks like this. They're really nice to us. They kind of give it to us in this form to start with. But we want to look at worst case scenario, right? We want to look at what's the worst they can throw at me, what's the worst that I might see on my homework. And so in that case, it might look like this, where step number 1, I'm going to subtract that 3 over to the other side. Then step number 2, I'm going to combine all of my pieces into one single simplified fraction. So I have one rational inequality, one single simplified fraction. So for these two pieces, I would need a common denominator of x minus 5. So I'm just going to multiply top and bottom of the second piece by x minus 5 to get that common denominator. I'll distribute my 3 here, so that'd be 3x minus 15. And the purpose of a common denominator is to be able to combine the numerators over that common denominator. Be careful though, because this was subtraction, when you combine these, you're going to distribute that negative all the way through that second numerator. So that would be a negative 3x and a positive 15. So watch out especially for that positive 15. So 2x minus 3x is negative 1x, negative 7 and 15 is positive 8, all over that common denominator. So now we've done step number 2. We've combined the pieces into one single simplified fraction. Step number 3, when you are working with a polynomial inequality, a rational inequality, you're going to set both your numerator and your denominator equal to 0 to get your critical numbers. Your critical numbers are where both the numerator and the denominator are equal to 0. Can a denominator actually equal 0? No, because 0 in the denominator is what? Undefined. So I'm going to make myself a little note here. Even though I have to set the denominator equal to 0 to get a critical number, I'm going to make myself a little reminder here. Hey, don't forget you can't actually be equal to that. Don't accidentally include that in your final answer. I'm even going to come up here when I make my sign graph and I plot my critical numbers on my sign graph. Just me personally, I'm going to put a little X on that, just so I don't forget to exclude that from my final answer. All right, so now we're making our sign graph. So we've got our critical numbers. I could pick a test point like 0 and plug it in. So if I come back and plug in here 2 times 0 minus 7 gave me the negative 7. And then 0 minus 5 gave me the negative 5. And then subtract the 3. So I end up with a negative value. So if it's negative here, when I cross a single critical number, does the sign change? When I cross a single critical number, does the sign change? Yes. So I'm going to have a sign change at this single critical number, and I'm going to have a sign change at this single critical number. So there's my sign graph. Now I'm ready to answer the question that they asked. They said, where is this less than or equal to 0? So what are we looking for, negative or positive? Negative, right. So we're looking for where it's negative or equal to 0. Less than 0, negative or equal to 0. So if I come back up here and look at this, I can see, okay, it was negative here and it was negative here. And typically if we say equal to 0, then we would include these 2 points. But remember, we've made ourselves a little mark here to not accidentally include that value because the denominator can't be equal to 0. So when I go to write my answer, for this first piece over here, I'm going to go from negative infinity up to positive 5. And even though this was equal to, and normally that would mean that I am using a bracket, because all the way along we've reminded ourselves, don't accidentally include 5 in your answer. You can't really be equal to 5. That would give you 0 in the denominator. That's undefined. Don't do it. Then I'm going to use a parenthesis here so that I am not equal to that value. For my other piece, we were going from 8 to infinity. There was no problem with the 8. That came from the numerator. That was perfectly fine. I don't have an X on that one. I don't have any exclusions on that one to worry about. So I could go ahead and use my bracket there and say from 8 to infinity. So one more time, when we got that answer, we were looking for where it was less than or equal to 0. So we were looking for the negative piece here and the negative piece here. So we went from negative infinity to 5, and we went from 8 to infinity. Those were our 2 pieces down here. We put a bracket with the 8 because this was less than equal to, and we usually use a bracket for that when it has an equal to. The only reason we did not use an equal to right here with that 5 is because that came from where the denominator was equal to 0, and we said that your denominator can never equal 0. So I cannot include that 5 as part of my answer. I can't be equal to that 5 because that would give me undefined. All right, last couple things that they finish off this section with actually are a little bit of a preview of something that we're going to look at in the very first section in the next chapter, and that deals with domain. So they want to give you an idea of where you're ever going to use this in math, why you would need to know this, and where it might come up. And so in example number 10, they asked me to find the domain of the square root of 64 minus 4x squared. Now, we're going to talk a lot more about domain in Chapter 1 and what it stands for. For right now, we're going to leave it at, we need to put in values for x that would give us real answers for y. If my answers have to be real, they can't be imaginary, right? And when I have a square root, I run the risk of imaginaries. How do I get imaginaries from a square root? How do you get an imaginary? Square root of what? A negative number, yes. So I need what is underneath my square root to not be negative so that I don't get imaginaries, right? So that means that what's underneath my square root can't be negative. It could be positive or it could be 0. It just can't be negative. So I'm going to take what's under the square root and I'm going to say it could be positive or it could be 0, greater than or equal to 0. And now we're back to the same thing that we've been doing all day today. And so that's an example of where you might need to use a polynomial inequality. All right, if you were solving that, we said earlier today for our polynomial inequalities, set it equal to 0 and solve, and the solutions that you get will be your critical numbers. So when I set that quadratic equal to 0 and solve it, I get 4 and negative 4. Those are my critical numbers. I'll come over here and I'll put those on my sign graph. Then I'll pick a test point, like 0, okay? If I take 0 and I plug into this thing, I'm going to get 64 minus 0, definitely getting a positive value. So if it's positive at 0, cross a single critical number, the sign changes. Cross a single critical number, the sign changes. There's my sign graph. So we wanted to know where this was greater than or equal to 0. So what are we looking for? Positives or negatives? Positives, right. So we're looking for where this is positive or equal to 0. So I want to give that middle piece right there between negative 4 and 4. That's where it would be positive. And where it would be equal to 0 would be at negative 4 and 4. So we're going to use brackets because we're equal to. And that would be the domain for that function. Now, if they asked me to find the domain for a cube root, you can't take the square root of a negative number, but you can take the cube root of a negative number, right? Like, what's the cube root of negative 8?
2.
Negative 2, right. What's the cube root of positive 8? 2. What's the cube root of 0? 0. So you can take the cube root of a positive, of a negative, of 0. There's nothing you can't take the cube root of when we're working with real numbers. So you can take the cube root of all real numbers. So if they ask you to find the domain of a cube root, it's always all real numbers, negative infinity to positive infinity. That's just a freebie. You don't even have to think about it. You don't have to write anything out. You don't have to solve anything out. If you have the domain of a cube root, it's always going to be all real numbers because you can take the cube root of anything. The restriction is on that square root. That was where we had to take what was under the radical and make it greater than or equal to 0. So when you're doing the homework tonight, 55 and 59 are going to be like these rational inequalities, and 63 and 65 are going to be like those domain problems. So here's our homework for tonight on pages 64 to 65. Pages 64 to 65. We're doing 45 through 51 odd, 55, 59, 63, 65, challenge 71.